everyone, welcome to this KANPUR-NPTEL online course on space environments and its effects on orbital spacecrafts. So, these days we are discussing the orbital debris and how to deal with the debris. So, we discussed the detection as well as the tracking, then capturing and the removal methods. So, in the last class we discussed two types of removal methods. One is the space environment based. So, space environment based means this technique where the effect of space environment like the atmospheric drag. So, the natural atmospheric drag was used and the ballistic coefficient was increased by increasing the area to mass ratio. So, if you increase the area to mass ratio, the ballistic coefficient value will go down and this will give you the rapid decay of the orbit. The other method we have that is the radiation pressure. So, this radiation pressure especially this solar radiation pressure can be tactfully used by proper control mechanism to produce the required drag to deorbit the debris. And we also started discussing the non-space environment methods. Today we will discuss a little bit more before we move to the next topic of that is the mitigation strategy of the different effects of the neutral space environment. So, this we discussed in the last class. This is the non-space environment based method. So, here it can be the contactless removal method or contact removal method. So, in the contactless removal method, as I said, there are the technique like artificial atmosphere influence method, then laser system, ion beam, shepherd and contact removal method, that is the slingshots method and the adhesive method. So, I will discuss each method one by one. So, the atmospheric influence method. So, here it is the use of a controlled and artificial gas environment. So, what is done here? So, you can increase the atmospheric drag on orbital orbits at high altitudes, where the natural atmospheric drag is minimal, to gradually lower their orbits. So, what is done actually by using this type of artificial that is the atmosphere, you can decay the debris, that is the orbital altitude can be decayed and it can re-enter into the atmospheric, that is the Earth's atmosphere. So, generally this is done at low Earth orbit where the most orbital debris exist. So, what is done here actually it fires focused pulses of atmospheric gases into the path of the triggered debris. So, these pulses increase the drag sufficiently to cause the deorbit rate to exceed the debris generation rate. And here it is also important to note that the pulse themselves it should fall back into the atmosphere, leaving no residual trace into the orbit to influence the operational satellites. So, this is the concept last class also I told. So, this shows that the pulse generator are placed on some balloon platform. So, this is this is an localized formation of the artificial atmosphere where the debris are there, the localized debris where you need to do the deorbiting or the removal of the debris. So, what are the components of this artificial atmosphere influence debris removal technique? So, first is the combustible propellant. So, here it utilizes a combustible propellant which can be either a solid or a combination of liquid fuel and oxidizer. So, when ignited, this propellant produces gases or particles that form the artificial atmosphere. Now, what is the propellant ignition device? So, depending on the type of the propellant, the ignition devices varies. So, for solid propellant, a laser may be used for igniting the propellants, while the liquid propellant require the combustion chamber, where the fuel as well as the oxidizer are mixed and ignited. What is the targeting mechanism? It includes targeting device that directs the combustible propellant to a region near the path of the space debris, and this ensures that the artificial atmosphere is created precisely where it is needed to affect the debris. And how the ejection is done? So, the combustion produces products are ejected into the path of the space debris, creating a localized artificial atmosphere. And how the momentum that is the management is done, because when it is firing that the propellant. So, what it can happen, it can create significant recoil of the momentum in the where you are making where you are using the platform for generating the propellant or the pulses of the propellant. So, what is done actually? So, system it includes multiple exhaust ports, and by ejecting the artificial atmosphere in opposite directions also. So, this system can balance the forces to maintain its position. So, this technique I will show you again when I will discuss another type how it is that you need to do a balancing action. So, that firing should also be done in the opposite direction. So, that the platform from where you are igniting the artificial the atmosphere the particles it should not destabilize itself. So, what are the challenges? So, the precision, controlling the influence precisely without affecting the nearby assets, and the energy demands. The pulse generation and beam system require substantial power, and the orbital mechanics. So, the orbital mechanics must account for how momentum transfer affects both the debris and the managing satellite. So, this is very important here. Now, the other method is laser based orbital debris removal method. So, in this this is the method, in the proposed method, the space debris are removed or it is it is controlled using the ground based or space based lasers. So, you see this is a ground based laser where the laser is targeting the target and the target is the debris. The other it can be on board a spacecraft. So, this one shows where it is this laser system is on board the spacecraft. So, this is your the debris, and so this can work like that. So, what is the core idea? It is to use the pressure from the photon momentum or laser evaluation to alter the trajectory of debris, eventually causing it to re-enter the Earth's atmosphere and burn up. So, this is the final goal, and this laser system which are used for this, it is available for both large and small piece of debris removal. So, the pulsed laser beam that shoots onto a space debris to decrease its velocity and lower its altitude. But here the risks is there, that is that it can generate the new debris by this laser beam. It can generate it can fragment the debris and makes many new debris, or it is small size debris. So, this is one of the disadvantage of this or the risks associated with this method. So, what are the key features? As I said, that is the photon pressure or the radiation pressure. So, low power, it can be continuous wave lasers are aimed at the debris. So, the momentum of photons, that is the light particles, transfers to the object, and over time this force gradually changes the debris orbit, lowering it until it re-enters the atmosphere. So, this is a time taking procedure, it will not be done very instantaneously. What is the advantages of this the low power the laser system? So, this is gentle, precise and does not damage the object, as we mentioned in the previous slide. So, there can be a risk that it can damage, it can make the debris into smaller number of pieces. So, that can be avoided by using this system. And what is the disadvantage? As I already said, it is very slow and it needs long engagement times and only works for small lightweight debris. So, this is the technique as I said, and the other is the laser ablation. So, what is done here? High power pulsed lasers heat a small part of the debris surface, and the material does the vaporizes, that is called the evaluation, creating a jet of gas. So, this jet of gas, it acts like a teeny rocket thruster pushing the debris in the opposite direction, and it is aimed correctly. So, this causes orbital decay leading to atmospheric re-entry. So, this is the concept shown here, how that is the laser pulse and you get the plasma flume ejection. So, this acts like a thruster. So, it becomes like a mini rocket. So, what is happening here? It is now pushing it in the opposite direction. So, actually the debris initial direction was like that. So, direction is being changed. So, all this control mechanism can be done in such a way. so that its orbital altitude is decreased and it gets deorbited. So, here the advantages is it is more effective on large objects and faster results as compared to this earlier where the low power laser system is used. Disadvantage is here there is the risks of fragmenting the debris and may raise legal military concerns. So, these are the problem associated with this. Now, the other method is the ion beam shepherd, or it is in acronym IBS. So, this IBS is a concept of ejecting highly collimated neutralized plasma beam into a debris object, thus lowering its altitude. So, here you are using the that is the plasma, that is a beam of plasma. So, ion beam shepherd is a spacecraft equipped with ion thrusters that fires collimated beam of ions, that is the charged particles at a target object. So, this technique is shown here. So, this is the debris. So, the debris is getting, so this plasma or the ion beam is thrown towards the debris target. So, I will explain this force thing. In fact, there should be a balancing force. So, this is F1. So, this ion beam transfers momentum to the object without physical contact and it allows for orbital repositioning. Then it can be used for the controlled deorbiting, then collision avoidance. So, this can be also used for collision avoidance, the orbit its path can be changed. The IBS spacecraft approaches a piece of debris and position itself nearby, but at a safe distance. Generally, the distance is between 10 to 100 meters. It activates its ion thrusters, directing a beam of high speed ions at the debris. The momentum transfers of the ions gradually it alters the orbit of the debris, that is lowering it to burn up in the atmosphere. And the IBS it simultaneously uses a counter thrust mechanism. So, counter thrust mechanism means whenever it is there is ejecting the thrust towards the debris. So, this thrust will push it to the backward direction because of this Newton's third law of motion. So, what is done in order to balance that, there is a counter thrust mechanism which is shown here. So, some more details is there in the next slide. So, whatever the force is shown here, like it exactly it does not the target, it does not capture it totally. So, what if this is because the plasma film expands downstream and the target eventually receives only a fraction of the total momentum. It cannot intercept the beam because the beam also diverges. So, as a result of that thing, there is a term called this transfer efficiency, eta b. So, eta b is defined as the fraction of the momentum captured by the target, or equivalently the ratio between the net force acting upon the target and the net force produced by the thruster. So, the thruster used to transfer momentum to the target is hereafter referred to as the primary thruster or the momentum transfer. So, as we have seen in the previous diagram, thus if F1 is the force transmitted by the primary thruster, then eta b into F1 is the actual force which is exerted on the debris or the target. So, this is shown here. So, you are having one force in this direction, this is F2. So, basically you will get here eta b then F2 minus F1. So, the force F1, as I already said, it reacts upon the IBS satellite and repelling it away from the target. So, this is very natural. So, what is done? So, if the IBS target separation is to be maintained, it is bound, then a secondary thruster also known as the thrust compensation thruster is needed. So, which is shown here. So, as I said, the thruster exerts force F2 on the IBS, which opposes the primary thruster such that the net force upon the IBS is F2 minus F1. So, now these are all about the contact legs. Now, there are the contact removal methods. So, contact removal method is the concept that takes the advantages of direct interaction between the chaser satellite and the target during the removal process. All these techniques are being discussed because the debris type and its categories, they are always different. So, you need different types of the techniques depending on the what is the debris, what is the size, and where it is. So that is why different methods are used, whether it is contact method or contactless method. So, there are two notable contact based techniques. So, one is the adhesive method, the other is, so what is adhesive method? So, adhesive methods they involve capturing the space debris using sticky materials. So, what is the key idea? It is to make the debris adhere to a collecting device, allowing for controlled deorbiting. And the other is slingshot mechanisms. So, this involves using a mechanical slingshot or thither based approach to impart momentum to debris. And this thither based technique already we have seen when we are discussing the capturing methods, that is the electrodynamic thither. So, it is similar type of thither is used here, and it is also called the gravity assist method. So, gravity assist. So, this technique is used so that this is aligned to the center, that is the Earth's gravitational force. So, in that direction it is directed by using this method. So, that is why it is called the gravity assist techniques. So, we will discuss now the adhesive methods for orbital debris removal. So, this method as already I told, it uses the sticky or the techy materials to capture or slow down small medium sized pieces of the space debris. Adhesive based systems they involve deploying satellite or spacecraft equipped with materials that can adhere to space debris on contact. So, the method is, one is the gecko inspired adhesive. So, you know what is the gecko, that is the lizard type, I will show you. So, these materials, materials is mimicking the microscopic structure of gecko feet that provide strong adhesions without leaving residue. So, you can see this is that the lizard, or this is the gecko feet. So, this is the type of the clamp, or this is the type of the contact removable. So, it is able to do it. So, this way the materials are developed. There can be electrostatic adhesions using electric charges to attract or hold the debris particles. Then there can be polymer based sticky surfaces using cold or hot melt adhesives or pressure sensitive polymers on robotic arms or panels. There can be aerosol or foam based adhesives capture debris by embedding into a soft sticky matrix, can handle multiple impacts and the spread force evenly. So, what are the deployment strategies? So, adhesive arm or NAT. So, a robotic arm or a deployable structure coated with adhesive materials to contact and collect the debris. And what are the panels used? So, this is the large area adhesive surfaces that passively intercept small debris as the spacecraft moves through the orbit. Then the swarm of miniature satellites, small satellites with adhesive skins that work in coordination to target specific debris. So, what are the challenges? The challenge is the durability. Adhesives must withstand the space condition, there is a space environment conditions, especially the radiation environment, then the thermovacuum, the temperature swings, that is the thermal and the vacuum conditions of the space environment. And the debris diversity, now varying size, shape and the material debris affect the adhesion performance. It may not work for each type of the debris. And there is here also there is the risks of secondary debris, poor attachment cold result in debris being fragmented. Control detachments. So, it is needed for safe release mechanism post capture, it may be necessary sometimes. The other method, as I said, this is the slingshot method. So, this is as I said, this is a thither slingshot methods. So, here what is done, a long strong cable that is called the thither is deployed from the spacecraft. It can be electrodynamic, that already we discussed. So, it will interact with the Earth's magnetic field and produce the the Lorentz force, or a momentum exchange thither. It can be a purely mechanical one. So, that it can align this the debris, that is the axis towards the that is the center of the gravity of Earth. So, then the Earth's gravity will assist it to deorbit. So, using the theta's, it swings the debris in a controlled arc and then releases it to the specific point in the orbit. So, this is the method. So, this maneuver can lower the debris perigee, that is the lowest point in the orbit, causing it to re-enter the atmosphere and burn up. And this method uses the rotational kinetic energy and the momentum conservation to change the orbital energy of the debris. So, the satellite may gain altitude or lose it in exchange, depending on how the energy is transferred. So, this is the all the these are the mitigation or the remedial actions for the debris, that is the man-made pollution. Now, we will discuss a few of the that is the mitigation and some techniques to deal with especially the atomic oxygen attack, which we started this topic of, that is neutral space environment, with this atomic oxygen. So, we will see that is how what are the mitigation techniques, as well as we will discuss how the design can be, proper design can be done, so that the atmospheric drag of the operating satellite or active satellites can be minimized. Okay. Of course, before that we will discuss the hypervelocity impacts. Already I said that the hypervelocity impact, so that are used by making the proper shield. When the size is less than 1 centimeter, you can use the proper that is the shield, or if it is more than that, then we can use one can use the that is either the maneuvering or avoiding the collisions by the methods what we discussed. So, what are the key mitigation techniques? That is shielding technologies. Already I discussed what is the Whipple shields. So, this consists of thin outer bumper. So, that already we discussed, that breaks up in the incoming particles before they reach the main spacecraft structure. The dispersed fragments then impact a secondary layer, reducing the likelihood of penetration, and the Whipple shields are effective against, as I said already, it can be used when the particle size is 1 centimeter or it is or less than that. There are the enhanced shielding available, so which uses the metallic foam or self sealing shields to protect against the micrometeoroid and orbital debris impacts. There are some simulation and testing methods. So, there is the code like hydro codes. So, this specialized computer programs simulate how the spacecraft shielding responds to hypervelocity impacts, allowing for optimization before physical testing. Then there is the equation, it is called the ballistic limit equations, VLES, and you already know I explained what is the ballistic coefficients. So, it is developed and verified through impact testing. BLEs help predict the threshold at which shielding will fail, guiding the design improvements. The design and the operational practices are, so identifying the critical components and their exposure to potential impacts enables targeted protecting strategies. Orbital debris mitigation guidelines are also there. So, generally you have to adhere to these standards, such as what is that interagency the debris coordination committee, that mitigation standards practices. So, this helps to minimize the creation of the new debris and reduces the collision risk. In fact, what are the guidelines we discussed at the very beginning when we are discussing the international cooperation or this IADC. Then monitoring and detection, that already I discussed, that what are the different ways of the monitor. So, there should be the impact sensors. So, in situ sensors can detect and characterize hypervelocity impacts, providing data on particle size, velocity, impact location, which are the vital for damage assessment and future mitigation planning. And the mitigation strategies against the atomic oxygen erosion. So, you can there are different types of protective coatings are used. So, one is silicon dioxide SiO2 coatings. These are widely used due to their transparency, flexibility and resistance to atomic oxygen attack. So, these coatings have successfully applied to protect solar arrays on the International Space Station. Then the other method is siloxane based coatings, so developed for their excellent atomic oxygen resistance, flexibility and crack resistance, making them suitable for protecting organic materials on spacecraft surfaces. Then the graphene coatings, graphene layers can significantly enhance evaporation resistance of materials like Kapton due to graphene's high impermeability and strength. Then gold and platinum coatings, these noble metals are are highly resistant to corrosion and are used to protect spacecraft component from atomic oxygen and other harsh environment factors. Then there can be the protective cover surfaces like beta cloth. So, beta cloth is a fireproof textile made from PTFE impregnated silica fiber used for the space suits and the spacecraft insulation. Its high tight wave and then silica content provides the resistance to the atomic oxygen exposure. Orientation, atomic oxygen attack is also can be minimized by orienting sensitive surfaces away from the RAM, because the RAM size of this spaceship or the spacecraft it will have the maximum the atomic oxygen so the sensitive those sensors it should not be put at the RAM size. So, and in order to minimize the glow, it is necessary to orient the remote sensing instruments like the optical sensor towards the spacecraft wings, that is the opposite to the RAM side or away from the surfaces that might glow. And there are also methods or also techniques by which the aerodynamic drag also can be it can be at the design stage, it can be taken care of. So, again it is the aerodynamic drag is controlled by the local atmospheric density and the shape size of the vehicle. So, what is done here in rare exception, raising the operational altitude in order to minimize drag is generally prohibited. Because it is this is due to higher launch cost, and there can be some this orbits, the altitude of orbits is for scientific the purpose it is fixed. So, you cannot go to higher altitudes. So, like the sun synchronous orbit like that. So, this is also so, and designing an aerodynamically smooth vehicle is usually prohibited due to the volume constraints imposed by the launch vehicle shroud. So, the drag is typically minimized by flying the vehicle in the orientation that minimizes the amount of normal surfaces. So, here this intention is that your ballistic coefficient should be higher. So, your the mass to that area it should be as high as possible. So, at lower altitudes orienting the solar panels at right angles to the RAM direction is a common technique. Of course, here one that it has to be kept into mind, that is electric power, that should be the optimum electric power of the vehicle. So, these are all the this methods and all those techniques related to the neutral space environment I discussed, and especially the atomic oxygen attack, then aerodynamic drag, then hypervelocity impact, then the debris. So, with this way we are concluding the neutral space environment, and from next session onwards I will start a new that is another type of the space environment, that is the plasma environment. Okay, thank you very much.